Can high schoolers understand AI? The answer is yes. Can they understand AI as thoroughly as professionals? The answer depends on how you teach them. I will present the basics of AI to provide a foundation for a positive answer. I will not delve into theory but rather focus on practical examples to help grasp the concepts. One of the simplest examples is linear regression analysis. First, let's clarify some basic concepts. The first one is AI. Artificial intelligence simulates human intelligence processes using computer systems, including learning, reasoning, problem-solving, perception, and language understanding. AI encompasses machine learning and other techniques like symbolic reasoning, expert systems, and rule-based systems. The second one is machine learning. Machine learning involves creating algorithms and statistical models to enhance machine performance on tasks using data without the need for explicit programming for each task. The third one is deep learning. Deep learning is a subset of machine learning that uses neural networks with many layers to model complex patterns in large datasets. Deep learning models require significant computational resources, often necessitating the use of specialized hardware like GPUs and TPUs. Let's also review linear regression and introduce some key terms used in machine learning. Regression analysis involves estimating the relationship between a dependent variable and independent variables by fitting a function from a selected family of functions to sampled data using an error function. It is a fundamental tool in machine learning for prediction. By fitting a function to available data, regression analysis allows for predicting outcomes for future or holdout data points. It is important to note that the parameters b and w are initially unknown. How can we estimate these parameters from a sample of data collected on x and y? The most common method used to estimate the parameters b and w is the method of least squares. This method involves minimizing the mean squared error, MSE, which measures the vertical distance of each observed response from the regression line. While there may be variations in the specific formula used to calculate MSE, the underlying concept remains the same across different implementations. The least squares method provides equations 1 and 2, which are used to determine the estimated parameters b and w. Regression analysis can be seen as a form of machine learning that utilizes data-driven techniques. We will now assume that a closed-form solution is not available, and transition from using a closed-form solution to using a simple neural network that employs the gradient descent method for numerical optimization. Gradient descent is a technique utilized to minimize a loss function by iteratively adjusting parameters until a local minimum is achieved according to a specific criterion. The process begins by setting the parameters to initial values and then updating them in the direction of the steepest descent of the loss values. Here the y-hat is the predicted values. In general, mean squared error, MSE, is just one of the methods to measure the disparity between predicted and actual outcomes. The functions that assess errors and facilitate parameter adjustments during training are known as cost functions or loss functions. Other examples include cross-entropy, commonly used in classification tasks. These functions are essential in enhancing model performance and optimizing algorithms like gradient descent, leading to improved prediction accuracy. When we use the model for predictions, w and b are constants known as parameters. However, when we use the loss function for minimization, w and b are treated as variables, while x and y are datasets that remain unchanged. The derivative of e with respect to w or b can be easily obtained from the loss function. Then W and B are updated along the negative direction of the gradients to minimize the error. Now, we are ready to start programming with Python. We will be using the Colab environment for our coding. If you are unfamiliar with Colab, you can refer to my previous videos or other online resources. Please note that you will need a Google account to use Colab. If you have a Gmail account, you already have a Google account. TensorFlow and PyTorch are highly recommended Python libraries for deep learning tasks. Let's begin by exploring TensorFlow. You may need to pause the video frequently to understand the code. The file name is specified. NumPy and Matplotlib libraries are required in this example. The variables x and y are Python lists, which are not efficient for numerical processing. So we convert them into NumPy arrays. The code calculates the values of w and b based on the previously mentioned equations. The regression line and dataset are then plotted. Next, we import the necessary tools for regression analysis using neural networks and define a list of layers. The sequential function groups a linear stack of layers into a model. In computing, especially in programming and data manipulation, the shape of a data structure refers to the number of elements along each dimension of the array. For example, a shape of 2, 3 indicates a 2D array with 2 rows and 3 columns. Shapes can also extend to higher dimensions. For example, a shape of 4, 2, 3 describes a 3D array with 4 blocks, each block containing 2 rows, and each row containing 3 columns. The model parameters can be printed, noting that bias parameters are also referred to as weights. The mean squared error is used as the loss function, and the optimizer atom is employed. TensorFlow requires the model to be compiled with the loss and optimizer specified as inputs. Each pass of the dataset through the algorithm is called an epoch, and in this case, we want the dataset to pass through the optimizer 200 times. When the fit method is called in TensorFlow, the minimization process is performed, returning a history object. The history object contains a dictionary with the key loss, which is used to plot the loss values during training. Finally, the model parameters is printed again. Let's run the code and examine the closed-form solution. The regression line is shown in yellow. Let's observe how the loss value changes during minimization. Here are the parameter values at the end of the iteration. In summary, the sequential API is one of the APIs TensorFlow offers for building neural networks. In general, machine learning requires an optimizer and a loss function. The atom optimizer is chosen for its efficiency and good performance across many tasks. In TensorFlow, particularly when using the Keras API, compiling the model is an essential step before training. Once compiled, the model is ready for training, where the parameters are adjusted to enhance predictions.